Welcome to today's lecture on the uh, conservation of mechanical energy. So, in the last class, we learned that conservative forces uh, are spring energy forces and gravitational forces. So, both these forces are conservative forces because uh, when a block is moved uh, between 2 points in a gravity, then the work done by gravitational force is independent of the path taken. By that, we mean is that let's say I have a block and the block is kept on a surface like this. So the block ends up moving when it is pushed on the surface, it goes down the surface. So the work done by gravity in let's say this path number one would be same as if we were to move this surface block uh, like this and vertically downwards. So in the path number two and path number one, the work done by gravity is same. So these kind of forces or such forces, when the work done by the force is independent of the path taken, these are conservative forces. So what is law of conservation of mechanical energy? The law of conservation of mechanical energy says that the total mechanical energy of a system remains constant if the internal forces are conservative and external forces do not work. So what is mechanical energy? Mechanical energy is nothing but sum of the potential energy of a system and the kinetic energy of the system. By system it means whatever particles and whatever bodies which we are including in a system. So let us take a case to demonstrate what is mechanical energy. The mechanical energy can be abbreviated as ME. It is written as sum of potential energy and kinetic energy. So potential energy of a system uh, and kinetic energy. How do we write potential energy and kinetic energy? So let us take an example. We have a block and the block is kept at some height h above the surface of Earth. So the potential energy of this block is simply mgh plus some constant c. So this constant c is the potential energy of the block at the surface of Earth, which we assume to be zero in the standard case. And let's say the kinetic energy of the block when it is at this particular height is half mv square. So we would say that the sum of potential energy and kinetic energy, that is mgh plus half mv square, this remains a constant when the forces acting in the system are conservative in nature. So here our system is this block and the earth on which it is moving. So this earth and block system, what are the internal forces to this system? The internal forces to this system are the gravitational force, mg, which is acting on this block. That is the internal forces to the system. So the internal forces are conservative in nature and external forces are to the system are doing no work. So for such a case, we can say the sum of potential energy and kinetic energy remains constant. So this is a very common case, and that's why we devise a law for it. So again, uh, conservative internal forces. This is conservative internal forces operate between parts of the system, and work done by external force is zero. And we can associate a potential energy in the system U. Then we would say this I stands for initial potential energy system plus kinetic energy of the system is equal to the final potential energy system plus final kinetic energy of the system. So let us continue with our example. So by this we mean is that uh, in the initial state, let's say the block is at some hi height uh, over the surface of Earth. So the law states that mgh at some high height plus the kinetic energy of the block when it is at high height, hi height over the surface of Earth would be equal to mgh. It, uh, it is at some hf height over the surface of Earth is equal to half mvf square. So this is the most common usage of this law. So work energy theorem also says something like this. Like the work energy theorem says that the work done by all forces on a system is equal to change in kinetic energy of the system. The work done by all forces can be divided into various parts. Work done by internal conservative forces, work done by external forces, and work done by internal non-conservative forces. So we are already saying work done by external forces to the system is zero, and work done by internal non-conservative forces is zero. And let us take the same case. Let us try to apply this example, that is the work energy theorem, to this case. So work done by internal forces, what would be the value of this particular expression? We know that work done by internal conservative forces would be simply mgh. Let's say the block has descended by some y distance, right? So initially the block was not moving, its speed was zero, and it is started moving somewhere here with some speed. So what is the work done by gravity? mg into the height which it has lost, which is mgh. So this can be written as mgy. So this work done by gravity should be equal to the change in kinetic energy of the block. So this should be equal to half m v square. So we can write mgy as the initial potential energy minus the final potential energy, and we can say that the block is losing gravitational potential energy, so its initial potential energy was higher and final was lower. So that's why we wrote initial minus final is equal to the change, because this expression has to be positive ui minus uf. So that's why we can write ui minus uf. So this is a very good way of writing change in any way. If the change is positive, then in the same way we adjust what are the initial and final values. So this is minus of delta u, and this is minus of delta u because delta u is the final value minus the initial value. So minus delta u is equal to mgy. So this implies minus delta u can be substituted over here. This value can be put over here. So minus delta u is equal to delta ke, or we can write delta u plus delta ke is equal to 0. So this means that the work energy theorem says the same thing which is said by the conservation of mechanical energy. That is, conservation of mechanical energy says that the sum of potential energy and kinetic energy remains a constant. And the work energy theorem says that work done by all forces is equal to change in kinetic energy. So both are uh, trying to say the same thing. It's just that from work energy theorem we have to uh, reduce these values to zero for conservation of mechanical energy to be applicable. So after doing all these calculations, what is our conclusion to our theory? The conclusion is we have an expression called mechanical energy, and that mechanical energy is nothing but sum of the potential energy and kinetic energy, and it remains a constant. When internal forces are conservative in nature and external forces do not work. So this is the most of the cases in our example. So this is what we said. That is the work done by all forces. That is conservative internal, non-conservative internal, and external is equal to change in kinetic energy. And this comes out to be the same as law of conservation of energy, which is for the general case that is mgh plus half mv square as a constant. So let us take an example. So we'll be taking these three questions. So the first question is we have a block of mass 10 grams. It is dropped from a height of 20 meters. Find its kinetic energy just before it hits the ground and 10 meters above the ground. So the first question mass is some 10 grams. So we know that initial potential energy plus initial kinetic energy is equal to final potential energy plus final kinetic energy. So initial potential energy is some 10 grams, that is 10 to the power minus 2 times g, let's say 10. It was at a height of 20 meters and initially the block was at rest. It was dropped. By dropping, we suggest that the block was not moving initially. Finally, the block is at the height of 10 meters. Actual gravity is 10 plus the kinetic energy which we have to find. Let's say it's K. So this would come out to be 1 joule. Similarly, for part B, the block has lost all its height, so its final potential energy would be 0 and it would be having some new kinetic energy K dash. So it has lost all its potential energy and all its potential energy is going into kinetic energy. So K dash would be equal to some 2 joules. In the second question, we have a case of a pan. The pan is massless. It is balancing a block of mass m supported by spring constant of stiffness k. The system is vertical at all times. Our objective is to find the compression in the spring at its equilibrium. The compression in the spring at its equilibrium would be simply mg is equal to kx. That is, the spring force is balanced by the gravitational force. The spring would try to keep the block balanced. It would apply a force in upward direction, and the block would uh, is experiencing gravitational force. So this would be mg by k. Next, we have to find the compression in the spring uh, when the block comes to that rest at first times. So what is happening here? Initially, the block is at rest, so its kinetic energy is 0. It starts gaining some kinetic energy, and at the point of equilibrium, all the forces acting on the block comes out to be 0. So would the block stop moving at that point? So that is one question you can ponder upon. So because of first law of motion, that is because of inertia, the block would keep on moving despite having no acceleration. The block would have gained some momentum and it would uh, keep on compressing the spring. So further loss of potential energy would again uh, transform into the spring energy. So we can write the potential energy in different forms. That is the change in potential in the spring, change in potential energy, gravitational potential energy plus change in kinetic energy is 0. So that is law of conservation of energy. That is the values remains constant or the change in these values remains 0. Sum of changes. So the change in spring energy is the spring energy is half k by square. It has gained spring energy, so that is positive. Potential energy is lost, gravitational potential energy, that is minus mgy, and kinetic energy is not changing since the block was at rest initially and finally it is at rest. So the value of y would be some 2 mg by k. So this would be the distance traveled by the spring before it comes to the rest. So as you can see, we can uh, see a very interesting idea that the distance traveled by the block up till the point of equilibrium uh, is just half of the distance it has traveled up till the point its speed becomes zero. That means it gains its speed up till this point, up till the point of equilibrium, and after that it starts losing speed. And just after it has traveled the same amount of distance it traveled from the initial position to equilibrium, it loses its speed completely. So this is our second question. In the third question, we have a block of some mass, let's say 40 grams. The block is placed on an incline which merges with the horizontal surface. We can read the question. A block of mass m is kept at height of 4.9 meters on an incline which curves and merges with the horizontal surface. At the end of the horizontal surface, there is a spring attached to the wall. Find the maximum compression in the spring. So we just learned what is conservation of mechanical energy. So what is conservation of mechanical energy? Total mechanical energy remains constant. What are the parts of total mechanical energy? As we saw in the previous question, mechanical energy constitutes of spring energy, gravitational potential energy, and kinetic energy. Can there be some other energies which can be associated with mechanical energy? The answer is yes. Other kinds of potential energy can also be associated with mechanical energy if they are conservative in nature and they are inside our system. So, one prominent example of this case is the electrostatic potential energy. So, what conservation of mechanical energy is saying is not all those calculations which we did, that how work energy theorem is equivalent to that. Work energy theorem is just one way of saying that there is, in some special case, we have conservation of mechanical energy. But in that special case, we encounter a lot of cases. That is a lot of kind of energies which we encounter. So it becomes a very common special case. So just like in this example which we have, this block is at a height of 4.9 meters above ground. It is lying on this incline and smooth incline. Spring constant is some 400 newtons per meter. So the potential energy of the block is going to be converted into kinetic energy as the block is moving and finally into spring energy. So can we write the equation directly? We can say the loss in the potential energy of the block is simply equal to the gain in spring energy. And at the final moment, when the block would stop moving, the spring would be having maximum compression. So that is what we want to find. What is the maximum compression in the spring? So we can simply say the loss in potential energy, that is mgy, is equal to half k x square. The mass of the block is some 40 grams, that is 40 divided by, to convert into to kg values, into 9.8 times the height which has the block lost, half k x square. So the value of this calculation, the value of x comes out to be some 9.8 centimeter. So this is what we want to evaluate, that what is the conversion of energy from one form to another. So this is what is the crux of conservation of mechanical energy. I hope you understood something in this lecture, and thank you for joining. Have a nice day.